Hi, dear student. We arrive at our next chapters, which is population and ecology. What is ecology? Ecology is a scientific study of all the interactions of organisms, not only with each other, but also with their physical surrounding, their physical environment. And the ecology will offers informations and a key to the survival of all the species uh, living actually, and also for their future generations. So it helps makes a very informal decisions about where we are and where we are going. So the current decisions can affect our life, uh, actual life, and the generations to come. Just so you can we can make it much clearer what we call populations and what we call community and the environment, the ecosystem. So a hierarchical level of organization, if I might remind you, that organism make species. Species came together to make the population, which is the same species, and the species can make a community, and this community is an interactions with their physical environment uh, ecosystem, and this ecosystem is a part of biosphere, which is a portion of the earth surface where the living things exist. So understanding how the organism, if we study the organism, how the organism adapt on their environment, then we go to population, how would we describe changes in a population over time, and then those populations at a particular local, how they interact with each others, and uh, and then those living organisms and their physical environment, which is the ecosystem, how the are contributing to the in the biosphere, how we contribute to the biodiversity and the dynamics of the biosphere. So the ecology can be both observational based on observations or experimental science, and therefore we emit hypotheses to explain and predict distributions and abundance of populations based on their interactions with an ecosystem. And the information can be applied to make more informed decisions about our survival, the actual time, or for the next, um, for the future. The environmental science and the conservation biology. Environmental science applies actually ecological principle to practical human concern, and conservational biology study all aspects of biodiversity. The goal is to conserve natural resources, including the wildlife, for benefit of a future generations. Human population has a clump distributions. So if I look at all the statistic, 60% of the populations people live in Asia, and most live in China and India. Mongolia has a population density of 1.2, no, 2.1 person per square kilometer. Bangladesh has a density over 1,278 person per square kilometer. So the industrial evolutions uh, because he increased the production. The industrial evolution came with an increased productions of food, jobs, health, um, discovering new medications, brought actually an increase in populations, in human populations. So the populations, it's increasing steeply. It increase rise the human populations, um, and the human population density tend to be highest on along the coast, and this making it go in a rapid growth. Even in the past, the human population has been relatively slow, but because of these industrial revolutions, the the populations became to increase steeply. So here in these two graphs, we have this first graph and then the second graph. Let's talk about the first graph. We plot a populations in a billion, as you can see here in the vertical axis, and you have the population billion from 0 to 2 with an increment of 0.5, and the year from 1200 to 1900 with an increment of 200, 1200, 1400, 1600, 1800 on the horizontal axis. The line began from 0.25 billion at the year 1200 and end at 2 billion at year 1900. The black plague disease is identified at 0.5 billion at year 1300. But industrial revolutions is identified at zero point 0.4 billion at year 1820 approximate. Modern science, industrial revolution almost at 1820, modern science at 1880. The second graph plot population in billion from 0 to 12 with an increment of 1, 1, 2, 3, 4 to 12. And then in the x-axis, the vertical axis have a year from 1200 to 2200 with an increment of 200. Line began from 0.5 billion at year 1200 and end at 9 billion over here. 9 billion, which is the lowest growth, and 12 billion, which is the highest growth at 2200. So the growth rate of populations is actually the difference between the number of people born and the number of people who died each year. So for example, we are going to cite an example so you can understand me better. If the current global birth is 18.5 per 1,000 per year, and the current global death rate is 7.8, per 1,000 per year. So the current annual growth rate is 18.5 minus 7.8 per 1,000, which is 10.7 per 1,000, which giving me 1.07% as growth rate. The next example is 14 per 1,000 minus 5 per 1,000, which is 9 per 1,000, which is 0.9% as annual growth for this town as the next example, as answer for the next example. So this concerns the rate of human population. So the future population growth is doubling time, is currently almost 60, about 61 years. What is double in time? It's the length of time it takes a population to double in size. Already in our world, we have they have area in the globe where people have inadequate access to fresh water, food, and shelter. So in 61 years, we need to double the amount of food, water, energy, and other resources to maintain the present standard of living. No need to tell you this, that the rapid growth actually begins to decline when resources become scarce. Not all the countries have the same growth rate. This map shows the projected population growth rate from 2010 to 2050. The data from the map is as follows. Portugal, Estonia, Latvia, Ukraine, Romania, Bulgaria. The growth rate is equal or less than 0.5%. Greenland, Russia, China, Poland, it's less than 0.5 to 0.001%. Let's look at where we are. United States. We're at 0 to 0.99% United States. United States, Canada, Mexico, Nicaragua, South Africa, New Zealand, Indonesia, Morocco, Algeria, South America. So do not all the country, we don't have the same um, growth rate. The growth rate, as I said over here, is going to be negatively 0.5%. That's the projections for those countries over here. For America, South America, some countries in North Africa, some countries in Asia, it's negative 0.5 to negative zero point 0.1. No, for the America, sorry, it's 0 to 0, almost 1%, 0.99. So yeah, not all, this is not all the countries have the same uh, growth rate. And even their industrial development. I mean, they have a people, countries that they are the more developed countries. We call that MDCs, and we have the less developed countries, the LDCs. So let's now compare this more versus the growth rate versus actually the more developed countries and the more less developed countries. The more developed countries are North America, of course, and Europe. So if you look at those, the populations growth is modest, and the people, most of them are enjoying a fairly good standard of living. The less countries, Latin America, Asia, and Africa, the population growth is dramatic. It's really dramatic, and majority of populations over here are living below the poverty. Nevertheless, I mean, the more developed countries did not always have a low growth rate. Between 1850 and 1950, their populations doubled, largely because of decline of the death rate. But nevertheless, they have only modest growth since 1950. Overall, the growth rate is 0.1%, but some countries are not growing at all or decreasing in size. The highest growth rate of United States, it's 0.8% due to immigrations, a large number of women of reproductive age. That's for the most developed, more developed countries. What about the less developed countries? The death rate began to decline rapidly after the World War II because of the inventions of the modern medicine. The birth rate remained very high. The growth rate of less developed countries, it's a peak at 2.5% between 1960 and 1965, the growth rate in majority of those countries has have not declined, and the population in those countries is predicted to jump to 8 billion by 2050. The majority of growth will be in Asia. Africa also has, however, high rate of death due to AIDS, the autoimmune disease. So let's look at this following what we call the age structure diagram. That's mean we are going to look at them by the birth or pre-reproductive, then the reproductive, then after birth, the post-reproductive. You can tell that the more developed countries, the MDCs, have a stable age of structure. The number in each category, which is the category that I said pre-reproductive age, reproductive age, and post-reproductive age, is stay the same. In European countries such as Italy, people are delaying childbirth or choose to not have a children or only one children. So in this case, there will be a decreasing in the population. Let's look at the LDCs. the less developed countries. They have the pyramid have like a pyramid shape over here. The age structure diagram is like a pyramid shape. The population will continue to expand even after replacement reproductions attain, as more younger people reach reproductive age. The increase in LDC population may be seen to be the main cause of a future environmental degradations. However, the MDCs, the more developed countries, are the ones that consume much larger percentage of the Earth's resources. Consumption leads to degradations. So we are going to look at now the environmental impact on the growth, on the population's growth. The environmental impact equal is the population size multiplied by the resource consumed by capita, which is the pollution per unit of resource used. So the majority of the less developed countries support the highest populations. What is the true, human population's growth? However, the current global death rate exceeds the current global birth rate. No, it's not. It does not exceed because after the Industrial Revolution, the population's growth is increasing. So the population that is growing, the population that is growing at a rapid rate will have an age structure diagram with actually highest number of pre-reproductive and reproductive individual compared to post-reproductive individual. So the human populations grow, the majority of the world live in Asia, okay? The black the Black Plague resulted in decrease of rate in the 1300 centuries. The change during the industrial lead to step rise in human populations. Human population density tends to be highest along the coast. This is how much we know so far. And what represent replacement reproductions is when the couple has only, they decide to have only two child, like United States. In this case, the population remained the same. The population will continue to expand when the reproductive age and pre-reproductive age, as I said, compared to the post-reproductive age, is higher in number, as you can see here in this slide. We got so far overproductions or overconsumptions in the more developed countries, overpopulations in less developed countries. Let's look at this environmental impact for the most developed countries. The first, this is three pies over here. The first pie chart showed the population most developed countries, 22%, and less developed countries, 78%. The second pie shows hazardous waste productions for the most developed countries, 90%, and less developed countries, 10%. The third pie shows consumptions of fossil fuels, 60% for the most developed countries and 40% for the less developed countries. Paper consumptions of paper, most developed countries 75%, 25% for the less developed countries. Metals 80% for the most developed countries, 20% for the less developed countries. So yeah, so we do have to cause some environmental impacts, some more. Those pies show really that the MDCs, the more developed countries, consume more than the less developed countries. So let's look at the characteristic now of populations. Various characteristics of those populations change over time. Periodically, it's subject to the, of course, like to the environmental instabilities. So the individuals are under the pressure of natural selections. The best adapted individuals leave behind more offspring than the less adapted individuals. So let's look at those natural selections. And to study this characteristic, we are going to look at the distributions and the density. The light, the water, the space, the food, they are resources. They are component of an environmental that support each living things. The availability of those resources influence actually the spatial distributions of those individuals. Three spatial patterns: clumped, random, uniform. Member of population are clumped within a range or portion of a globe where species are found because they are localized in an area suitable to that fit them to their growth. The the population density, which is the number of individual per unit area or volume, they are of course very high when there are plenty of resources around. Penguin example, that defend an area around their nest, their theory complete a circle on the nest with approximately zero point 0.5 meter radius. Um, if each nesting penguin has the same size and has the same shape territory, what type of distribution those animals exhibit? They exhibit what we call an uniform distributions. So the density of a population, so for example, over here in this example, we have a prairie dog that live 750 animals live in all 500 meter square area. What is the population density? If we take my calculator, 700 divided by 500 is going to give me 1.15 as a density. That's the density. So just to remind you, a population that has a negative growth rate is when the death exceed the birth rate. That population has a negative growth rate. So as I said, the pattern distributions can be either clump, the small, like here an example for those desert shrubs that they stay, the young small ones stay together, remain close approximately to each other, so they are clumped as distributions. They are either, they can be randoms and they can be uniform. They make a circle around the nest with approximately the same distance, each strap, same size, same shape, territory coming together, same shape, same size, same shape, territory, same distance, or randomly. We already talk about that, that when the population growth exceed, the birds exceed the death. The population shrinks when the death exceed the births, and all this depend on the resource demographic influences on the growth rate of the populations. So let's go back to this age structure diagram again, because we are going to talk now about the demographic characteristic, the birth exceeding the death rate when pre-reproductive and reproductive individual outnumber the post-reproductive. So this, as you can see over here, the increase in populations shows that the pre-reproductive and the pro-productives outnumber the post-reproductive individuals. The age structure diagram for decrease in population show that the post-reproductive individual exceed the pre-reproductive and reproductive individuals. Stable populations shows that the number of pre-reproductive, reproductive, and post-reproductives are approximately equal. How now we are going to talk about the survival curves. How the age at death influences population size. So we have from age to 0 to 1, 1,000 number of survival beginning, and then the number of death during the year is 199. So 1,000 to 199 is giving me 800, 1 at the age 1 to 2. 1 to number of the death, 8 to 12. So 801 to 12, it's 782, etc., etc. So this will mean the number of individuals that live or die at each age. And the doll ship, it's a good example. At the age 14 to 15, there are no survival because the number of survival 3 to 14 is 3, number of death is the 3, 3 minus 3, it's a 0. That's a survival ship between death and between survivor and death. Let's continue with this survival curve. So let's plot those number of survival by 1000 per against the age. So in y-axis, we put the birth number of survival, and then the percentage of the lifespan, 0, 50 to 100 year. Very high survival rate, and then after when they reach the old age, they start decline. Type 2, that it happen equally at any age. Type 3, the death is almost among the young with a few individuals that reach the old age. So the curve depicts organisms that have an equal probability of dying at old age is type 2 survival. Type 1 survival is the survival rate is higher, but they die at old age. What's meant by an organism biotic potential? It's the maximum rate of population growth with unlimited resource. This is unlimited resource. This is what's mean by eutics. And this is my next biotic potential, highest potential rate of an increased populations where resources are unlimited. Whether the potential is high or low depend on demographic characteristic of population, availability of resource, number of offspring per reproductions, change of survival until age of reproductions, how often each individual reproduce, and age at which reproductions begins. The biotic potential for mice is very high, produce many offspring that reach maturity quick, but for the rhinoceros is very low. Only 1 to 2 offspring per any infrequent reproductive event. So the pattern for population growth depend on those, as we call biotics potential, which is the availability of unlimited resource, number of offspring per reproductions, change of survival and the age of reproductions, how often each individual reproduce, age at which reproductions begins. This depends on two fundamental patterns. It's either exponential growth or logistics growth. Exponential growth or logistic growth. Exponential growth is the curve have like a J shape curve. We have a lag phase. The growth is slow due to few individuals, and then it starts growing very accelerating growth. This is what we call the exponential growth phase. And this can continue, remember, we're in biotic, as long as the resources are unlimited. A caterpillar, he is shown near this graph because he has an exponential growth. Logistic growth. It results on an S-shaped growth. You have also lag falls, which is growth slow with few individual. Exponential growth accelerating. But we have what we call decelerations phase. Rate of the population growth due to the competitions for resource. So here in this graph, we have number of organisms on the vertical axis and the time on the horizontal axis. The dashed line that you see in the top over here is from high number of organisms that run parallel to the horizontal axis, and it's identified as carrying a carrying capacity. Carrying capacity is the total of individual that the resource can support. And this number cannot be constant and can vary with under some circumstances. So the curves began at the origin and identified as a lag. And end with a high number of organisms. This is the G-shape curve. There are another curve also that starts also at the origin and increase with time and experience exponential growth in the beginning and then logistic growth. With which the curve reach a wave pattern that is identified. This wave patterns that you are seeing is identified as a stable equilibrium. The difference between the G shape and this curve that reach this stable equilibrium, it's called environmental resistance. A fish is shown in this graph to cite an example of this type of logistic growth. The next graph it's an application of logistic growth knowledge. The human is using a fish population as a food source. Want to maintain this fish population in exponential growth rate phase. Overfishing may push the population into lag phase that take years to recover. So let's talk about this graph. The graph plot fish calf are remaining in a million of tons on the vertical axis per year. From 1950 to 2010, an increment of 20 on the horizontal axis. The data from the graph are as follows. A line of amount of fish caught beginning at 2.5 million tons at 1950. and end at 1 million at 2010. Why he peaked actually at 3.2 million tons at 1975, 65, 65, before 1970, the peak. That was the amount of fish, Kath. The other line, this green line, that's the red line. The green line is the amount of fish remaining. It began at 3.1 million at 1950 and declined steadily until he reached 0.1 million ton in 2010. So overfishing pushed the population in a lag phase that take years to recover. If populations is trying to reduce the number of pests, it is better to reduce the carrying capacity rather than reduce the population size. So it's better to encourage the exponential growth. Factors then that really regulate the population's growth are living, both biotics and abiotics, not living compound. Those are the two major factors that regulate the population size. The density independent factors, abiotics, such as weather, natural disasters, can cause sudden and catastrophic reductions in a population size. The intensity of effect does not increase with the increased population size. The density independent effect. Abiotic factors, as I said, weather, natural disaster. Two populations of field of mice are in the path of a flash flood. Low density of mice with 60% of death rate. The 3/5 mice drown. Same way, remember that this is independent factors. Two population field of mice are in the path of flash fall. 60% of that rate, low density of mice. High density population has 12 of 20 mice drawing. 60% of that size of population did not change the death rate. It stays 60%. With high or low density of mice, still have 60% of death rate. So the density is independent of the abiotic factors. Now let's look at the density dependent. Competitions, predations, parasitism, that's the biotics factors. The percentage of populations affected does increase as population densities increase, and the intensity of effect increases as density increased. What's mean competitions? In when they compete to use the same resource like light, food. Let's look at those wood keepers. They compete for nesting size. Each pair require a tree hole to raise the offspring. If there are more holes than pairs, every pair gets a hole. If there are fewer holes than pairs, some pairs do not get a hole and do not reproduce. So here, the density depends on the biotic factor, which is the competition for an habitat, for their little place to live, which is for those wood pickers, it's a hole in the tree. The intensity of effects increase the density. Other dependent factor that we can cite is the predations, like predators eating the prey. Lions kill zebra, blue whales eat strained quails, deer eat leaves. So the effect of predations also increases as the prey population density increases. The prey easier to find when hiding places are limited. The mice might have a hole to hide in to avoid being eaten. If there are 102 mice by only 100 holes, two mice are in the open space. If neither is eaten, the predation rate is then 0%. Cool. But if there are 200 mice and 100 holes, and only half of 100 mice without holes, the predation rate is 50%. Increasing the density of prey has increased the proportion sprayed open. However, some predators and prey populations increase and then decrease in population size. Famous example are the Canadian lynx. This graph shows the the predator prey recycling of a lynx and the snowshoe hare, which is kind of a rabbit, this white little rabbit over there. The graph plots a snow hare per hectare on the left vertical axis from 0 to 5 with an increment of 1. The length tracked per 100 kilometers on the right vertical axis from 0 to 100 in increment of 20, so 20, 40, 60, 80, 100. Any year from 1986 to 2009. So the graph is as follows. The snow hare per hectare spike at 2.6 and 19. The snow hare is what is red, and the tracked per kilometers is in blue. So it spiked almost at 1989 at 2.6 snow hare per hectares, 2.7 in 1998, 1.2 in 2007, the length tracked per kilometers is around 2.7, 1992, almost 4 in 1998, so almost 1992, almost around 50, 80, 1998, 40, 2007. So the lengths decrease the hare populations. Study has found that if the lynx denied access to the hare, cycling of the hare population continue based on the food availabilities. So this observations pattern is based on both hair food cycle and length hair cycle. So here the hair show populations reach a peak a year or more before lynx populations. So it reached the peak before the lynx, if you can see it, or within. Then they reach the peak over here, then the lynx reach the peak. Extensions, two patterns of life story, the opportunistic life and the equilibrium life history pattern. The opportunistic life history patterns tend to exhibit an exponential growth. The number of populations are small in size, mature early, have a short lifespan, and provide limited parental care for a large number of offspring. They tend to regulated by density-independent effects, and the population has high dispersal capacity. Example, insect and weeds. So the opportunistic patterns, the small individuals, short lifespan, fast to maturity, many offsprings, and little or no care of the offspring. Those have a tendency to exhibit exponential growth. And here are to be regulated by density independent effect. Those weeds. Equilibrium pattern. This does not exhibit an exponential growth, but a logistic population's growth. Size of the populations remain close to or at carrying capacity. So this is why we said equilibrium pattern. The member of the populations are large, slow to matures, have a fairly long lifespan. Here, the growth is regulated by density-dependent effects and tend to have low mortality rate because they have much care of offsprings. So yeah, this is a logistic populations growth because the growth curve exhibits both exponential growth and the stable equilibrium phase. We're arriving almost at the end. The extensions of the total disappearance of species or higher group, the equilibriums of species are more apt to go extinct because the size of geographic range, degree of habitat tolerance, and size of local can help determine danger of extinctions. And those are the most common species that they are at risk of extinctions. So this shows some species, their habitat chance and cause of their extinctions. The chance and cause extinctions are higher against each species. Galapagos medium ground finch, he need a Monterey pine because he have a restricted geographic range. So therefore he have a broad habitat tolerance. The California gray well, the cotton's Fremont wood, so we have a narrow habitat tolerance. The tiger, grass fern, and also it's a small local populations too. The fish crow is have a restricted geographic range, narrow habitat tolerance with a large local populations. The Tasmanian devil, a restricted geographic range, broad habitat tolerance, and small local populations. Those are the several causes for their extinction. The mountain gorilla, he have a restricted geographic range. He have very narrow habitat tolerance and small local populations. The spotted owl, extensive geographic range, but narrow habitat tolerance and small local populations. Those are the causes for that will eventually cause um, lead to their extensions. They are very vulnerable to extensions. So that's end our chapter 30. It's been recorded. I will post the recording shortly.